Yeah, Vlad, you can take it away.
Okay, great. Hello, everyone. My name is Vlad. Today we're going to talk to you about reinforcement learning, and we'll show you a little example. Let's take a look at our plan for today. So we will start off from talking about some reinforcement learning basics, and then we will look at some theory that regards some specific reinforcement learning algorithms. And finally, we will transition into implementation of a specific RL algorithm that will learn how to play Pong just given pixel data and reinforcement, basically from the environment. So reinforcement learning fundamentals. Let's go. Yep. What are some basic reinforcement learning problem features? We may usually expect the reinforcement learning problem to have some sort of interactive environment, some sort of agent that will be controlled by our model that can act on an environment and transition it to new states. And the goal of our agent will typically be to maximize some sort of reward given to us by our environment. So let's see, can you guys guess or do you guys have any ideas what sort of examples and what sort of typical RL problems there can be solved by these RL algorithms? You can type in the chat or say. Yeah, right. We're looking at games. Games a lot. Any other ideas?
Self-driving cars. Sorry.
That's a good one. That's a game too. Yes, that's a very hard game. Yeah.
Yes, very hard game.
Yep.
So
let's.
Robotics uses reinforcement learning a lot.
Yes, this is a good one, and this one finds some applications. It's getting more popular in robotics right now. You can basically teach a hand how to manipulate some sort of object. You can present it with an environment and give it a reward when you see that it does what you want to do. So let's take a look at some of interesting examples here. This one is actually the one that raised an interest in reinforcement learning in 2014, I believe. Here the agent learned how to basically play this game using only pixels and the reward that is provided by the game. So basically he was able to find this interesting strategy of getting this ball around so that it scores more points.
What was this game's name for those who don't know?
Yeah, this is Atari Breakout. Thanks for pointing out. And it was actually the same algorithm was able to successfully learn several other Atari games. So sort of this similar 2D environment using only pixels and a reward. Let's go to the next one. This is a more complex example. The game of Go is considered to be a very complex game itself. It's considered to be way more complex than chess in the sense that it is much harder to evaluate what will be your reward in several steps of the game. So you have this huge board, 19 by 19, and basically it is very hard to brute force compute your way to understand what next move you should play. So This was successfully solved by Google in 2016. We see here world champion in Go. Basically, the algorithm was able to win for 4 or 5 games against this world champion. This is which is considered to be a pretty remarkable achievement of reinforcement learning. So let's go next and see why do we want to use RL typically? So basically we want to use RL when we can't really solve the problem using supervised or unsupervised learning. As you see, the environment is pretty unique and it is pretty hard to get the true states. For example, if we're talking about the supervised learning, you can't really get true labels for it. And we also might want to use reinforcement learning because these unique problems, we already have a framework, some sort of framework on how to efficiently approach them. So that makes solving the problem not much easier, but solvable. So let's take a look at exactly how reinforcement learning differs from supervised learning and unsupervised learning. So basically, reinforcement learning can be viewed as its separate branch compared to supervised and unsupervised learning. As I mentioned, you will not typically have true labels for the states in the reinforcement learning setting as you would have in the supervised setting. In the same way, you will also, in order for your agent to be successful, you also need some sort of a metric to know how well it does. And this is done by a reward function that is basically replaces labels in supervised learning. And the other interesting fact is that in reinforcement learning, you don't have a complete and finished data set when you start training. So you will need to instead gather it. It will need to be gathered by an agent. And this is a separate task that is called exploration, and how successful the agent is will really depend on how well it can explore the environment and how well it can basically collect this data set of possible sets of possible states and state transitions. So let's go forward and see. By the way, actually ask if you have anything is unclear, or do you have any questions so far?
I have a question on the previous slide.
Yes. Let's go back there. Yeah.
So when you say a complete data set is available, does that mean that we do know all the information of the environment?
So
or
basically,
learning isn't a part of reinforcement learning?
Could you please repeat that? Basically in the supervised and unsupervised learning, we usually have this complete data set that we can train on. And in reinforcement learning, our interaction with environment, the interaction of our agent will determine what sort of information we know about the environment. The structure of the data set, so what sort of features we have, for example, may be predetermined. So is that what you're asking? What's the input for our reinforcement learning agent?
Who asked the question?
I guess he's gone now, so we can
Okay.
consider the question answered for now.
Mhm.
Okay. We'll return to that if
Like, I guess I'm just not completely clear. Like, so, like, do you really, like, would you say you have like a data set in like a pure reinforcement learning sense because it's like an environment instead of like specific data?
Oh,
so it will be an environment here will be like a dataset generator basically, but we will need to whereas in the supervised setting you might have all the data that you need sort of in order to do well already. In the reinforcement learning environment, you will need to act in such a way so that I guess you collect the experience of a more representative experience that is more representative of an environment. For example, if you just if you have an environment where you just sit in a corner, you have a room and you just sit in one corner, you don't explore the rest of the room. You don't really have a full data set of what being in every possible position in that room, what kind of reward will be given by being in any sort of state in that room. Does that make sense?
I can actually expand on that. So,
Okay.
yeah. So, yeah, what Vlad was talking about is, in supervised learning and, traditional classification, usually you have data sets with clear labels. Like if you're trying to decide between a cat or a dog, right? You can easily go on the internet and find a bunch of pictures of cats and dogs, and you can clearly label them as cats and dogs. And there's a right answer. But for reinforcement learning, if you're addressing a problem such as a game, like FPS game or first person shooter or something, you can't necessarily label put states of the game very easily. Like, how can you tell what state you're in is a good state to be in or a bad state? Or even in like chess, right? It's very hard to get all this data fully mapped out and labeled. So in this case, reinforcement learning kind of gets around that by not labeling the state, these state inputs at all, but just generating a bunch of them by having the AI play the game. And then instead of labels, we give it a score. So let's say, you take a piece, that's a positive thing. So we want to give it a positive score. But if we get our piece taken, that's a negative thing. So we get a negative score as feedback. So that's kind of the approach reinforcement learning is going for here.
Okay, thank you.
Okay, let's then go to the next.
I have a question.
Yep.
So what is unsupervised learning, and how is that different from reinforcement learning?
I can actually explain that. So unsupervised learning, similar to reinforcement learning, usually you don't have labels, and the main thing people think of when they think of unsupervised learning is clustering, which can be simplified into you basically classify rows into groups based off of some distance function, and then you sort of group them like that, even there's no specific label for a group or anything like that. It's used for, like, you can use it as pre-processing, but it's usually just kind of separate from supervised learning and reinforcement learning. Does that answer your question?
Yeah, that makes sense.
Thank you, Gaston.
Great questions. See anyone else? Okay, let's just go for the next one. Okay, so some of the key concepts in the reinforcement learning, and basically how we determine how our agent and how our models is built is we may have some sort of policy, and that will determine what action it makes sense to take based on the state that we're currently in. Also, some useful concepts that reinforcement learning defines is state transition probability. This basically determines what is the probability of getting to some other state based on current state, based on any given state, basically. And you can calculate that in the future, basically recursively, like I'm getting one state and then so on and so forth. Value function is something that can basically estimate the reward of being in any state based on this transition probability. So, for example, I know that if I stay in state A, I will get a reward of 1, and also there is a probability of 90% of returning to the next state. This is not taken into consideration any actions yet, but a Markov decision process is something that adds these actions that we can take in any sort of state, and basically computes the value. Basically, doesn't really compute the value, but explains to us what is this graph of the model of the environment that we have. So here we have, for example, 3 states, and in any state we can take 2 actions, 1 or 0. And this one will define what are the probabilities of, if you take action 1 or action 2, of getting in a state, in one state or in a different state. And based on this knowledge, you can see here some state transitions are associated with negative reward or positive reward. Based on this notion of Markov decision process, you can infer and sort of determine what will be a useful policy in this case. What is the best set of actions that you can take if you're in state 0, or if you're in state 1, or if you're in state 2. Does that make sense? Any questions so far on that? It's a very big topic. Actually, Markov decision process, we will have a link after the presentation is done. This is basically the basis of the reinforcement learning.
How much of an effect does the probability of an action have relative to its reward? Like, for example, if you have a transition that has a very low probability of occurring, but the reward is significantly higher compared to the other options, would the policy just choose that, or would it choose something that's more likely to happen?
It's a great question. So this is basically, this is something that we can play around in specific implementation of the policy, of any specific policy. So some policies may prioritize really exploration. So this will be really trying different states, maybe maybe not necessarily actually with your example, but some policies might try to go for the less probable, let's say, actions, and some of them will try to be more safe, and go with more probable way, I guess.
I can expand on that a little bit. So what Gaston has, I guess, brought up is a pretty big issue in the whole reinforcement learning thing. It's called the sparse reward problem. So basically, like, if you define how you get your reward too sparsely, your model might just never get that reward, and so they'll never learn to try and deal with it, right? So that's just up to you defining the constraints of your problem to try and solve the issue. You know, you have to define your reward function to try and reinforce the methods you want to you know, the model to get better at, and how you distribute the rewards can really affect that. So it's definitely a big issue, like Vlad was talking about.
Exactly. Any other questions so far? If not, we can go to the next slide. So we can see what would be some sort of terms and in this specific environment and in this specific time frame for this agent. We have an environment that is this game, this called stream, an Atari breakout, that basically defines what sort of actions you can take here, your action space. So you can either go left or you can go right. You can go stay on one spot and don't move. The agent here will be the model that controls this little sprite on the bottom. We'll tell it where to move, either left, right, or do something else. The action is something that's the model gives us as an output right now at this current frame. So, for example, the right, and the reward here is, for example, this thing on the top. Actually, this one is an in-game representation of reward, and it's not necessarily the something that we want to give to our agent, because we also want to give them a notion of, for example, not catching this ball. For example, give it -100 for not catching this ball if it does so. Let's see, and observation. Well, observation is just the current screen. For example, all the pixels that we have here. The state that we will feed to our model can be something more complex. So, for example, several pre-processed observations. In order, for example, it's hard, for example, for us to see whether this ball right now is it going up or is it going down. So we might want to use several screens so that we can see the trajectory of the ball, where it is heading here. And that will be our state. Let's see. Yes, and the episode will be basically one playthrough of this game, this Atari game. The playthrough until we finish the level, or until we lost or all our lives, basically. Typically, we will train or update our agent at the end of the episode when we have the complete set of data. And let's see. Is that clear? Any questions so far on that?
Looks good.
Sounds great. Then we can transition to our next part. Denny, come to you.
There are three reinforcement learning techniques known: SARSA, Q-learning, and policy gradients.
Wait, to
The
confirm, it's
former
like
two-
just the three we're covering today, right? Those are not all of the RL algorithms in the world.
Definitely not.
We can talk about the other algorithms like next semester or something.
Sounds great.
Yeah. The former two rely on something called a Q function, where a Q function evaluates the results caused by a state action pair to see how close they are to a goal set by the designers of the algorithm. If you do this to many action state pairs, you can put them into a table of Q values. Q stands for quality, which is a term referring to the results made by the Q function. Does anyone have any questions on the Q function? Okay. If you look at these two equations here, you'll notice that the equations for SARSA and Q-learning are pretty similar. With what the only exception is the function being multiplied by gamma, which is written as a y here because keyboards. In SARSA, gamma is just being multiplied by the quality, the Q function of a future state action pair, or as they're written here, S prime and A prime. Q-learning, on the other hand, multiplies gamma by a function representing the best possible future Q value.
Any questions about this? Because this is these equations are kind of mathy looking, so don't be afraid to ask questions.
So is there, like, in the most general sense, a very slight difference between the two?
Yeah, so it's just kind of like a difference in the I don't know what you call it, the ideology. So this function represents how you update the Q values in your Q table. So you use the previous Q value and the Q value you have for the next action and state pair that you have, and you use that to sort of update your previous Q value to, let's say, a more correct state. So
three slides from now, you'll be able to see pseudocode, which shows exactly how the slight difference, shows exactly how they both work.
yeah.
Basically, that slight difference actually matters a lot, as you'll see in the next three slides.
Yeah, but the general ideology is Q-learning always takes the action that looks to give it the best reward, while SARSA will follow its policy, whatever the policy spits out, which is kind of like its strategy for picking the next action. So that's just the general difference between the two ideologies. But as you can see, they're very similar, like Daniel was saying.
Question, what is S prime and A prime?
Right, so S and A by themselves represent the current state you're in and the current action that you took. And S prime and A prime represent the next state you would be in if you took the action A prime.
Got it. Is there any sense of time in this Q table?
So
It's more like a turn-based programming.
Got it. It's like a board game.
It's more like present to future, then the future becomes present, then goes to another future.
Yeah, so you can think of the time step as, you were in one state and then you're going into the next state. So that's kind of like you're stepping through your environment with actions, and that can chronicle a passage of time, I guess.
Got it. So in this setup, if you're in a state at time 1 and then you reach the same state at time like 80, then it would have the exact same Q value, right?
Yes, unless it was updated, somewhere in that time, because these functions are meant to update the Q values for those states. But
Right.
in general, yes.
I find that interesting because when we think about, say, like if we're trying to get to the airport, and then we get to the airport in 5 minutes versus in 30 days, is a big difference. It seems that this assumption here is taking out that time component.
Yeah, so that is a good observation. Yeah, I think
But
it's
it does
because
make sense in like chess or something.
right. Yeah, definitely.
Yes, make a comment on that. Sometimes you may want to add some sort of reward associated with time, some sort of negative reward.
Oh,
if you want the agent to learn, to do something quickly.
Vlad,
So like,
Vlad brings up a good point, because that R in the very beginning of the function does reference the reward. So that could be different according to, if you get there in 5 minutes or 30 days. So that is a good point. I almost forgot to bring that up.
Cool.
Now we'll get to the differences. SARSA determines what future state in action it's going to analyze based on its previous policy. The theory is that eventually it will look at what it's doing and then change the policy to be better until it eventually stumbles upon an optimal or almost optimal policy. How it looks through influences the policy. On the other hand, Q-learning does not use its policy to determine which action to take. It just looks at all the state action pairs available to it and chooses the one that will lead to the best possible response. This thing is supposed to go directly to the best solution, but since in many cases there isn't a best solution, it mostly just gets to a better solution. Neither its policy nor its policy the policy it starts with does not affect anything. It just goes straight for the best possible response. It's trying to go for the best possible response.
Yeah, it goes for the maximum Q value of all the actions presented to it. So whatever action returns the maximum value, it'll just take that one. So it's kind of like a greedy approach. Any questions so far? Okay, I guess you can move on.
These differences also lead to weaknesses. It is very easy for SARSA, for instance, to get stuck on local extrema, since it's just following its previous policy, not directly going for optimal Qs. Furthermore, since it's following its policy, if it has a bad policy, it will take time for it to figure out that its policy is a bad policy, because it'll keep on making bad choices until it learns that those choices were bad. In many cases, this could result in SARSA never getting the best policy, only something close to it. On the other hand, since Q learning has to look at every possible state action pair and find all their qualities, it can take quite a bit of time to look through all of these and figure out something. Furthermore, since it looks through everything, it has a higher chance of getting something bad, which can, yeah.
Okay. Does anyone have any questions for that part?
Oh,
Are the policies different than SARSA and Q-learning, or are they policies? Because you mentioned that starting with a bad policy can take a very long time to make progress. So does that just mean you start with like bad default values, or is it something separate from SARSA and Q-learning?
okay.
Yes.
In both cases, you can start out with a bad policy, but Q-learning goes directly for the Q-learning does not decide where to go next based on the policy it has. So if you start out with a bad policy, Q-learning will quickly get out of it. On the other hand, if SARSA has a bad policy, it's going to keep on following that policy until it learns through trial and error that policy was bad and try.
Yeah, so let me expand on that. So basically, that whole Q table thing we were talking about earlier, that is initialized to random values at the start. And basically, both these algorithms kind of use that to, they're trying to update the Q values from random to, you know, values that will give it the optimal strategy. The difference is SARSA uses those Q values directly to pick its next action. But Q learning, since it always takes the action with that gives the maximum Q value, I guess, progress or update, it kind of ignores what the strategy is telling it to do at the beginning, and it'll just update the strategy based on its greedy approach to taking the maximum Q value. So that's just the two different ways they try and update their Q table to the, I guess, optimal state. Did that answer your question, Gaston?
Yeah, that answered it.
Yeah, it's kind of like in traditional machine learning, how you kind of start with like randomized weights, and then you just try and find different ways of optimizing those weights to give you the better solution.
Does the policy have to be random if you have like a good idea of what they can be, or I guess it's dependent on each, like on the given state, right?
Right. Yeah. If you have some prior knowledge of, you know, what a Q table would be, then you could definitely like manually input it yourself, I suppose. Just like you can do that kind of with traditional machine learning. Okay. So I guess we can move on.
Finally, we're going to look at this pseudocode. This pseudocode in particular refers to SARSA, but if you just swap out the equation on the fourth line of the loop, you will, with a Q learning equation, you can change the pseudocode to a Q learning pseudocode. As you can see here, you'll first notice that it will first fill out the Q table randomly, just so it can actually go on and do something. Then it will pick a state and an action using that table, and it will see what will happen. If what happens is something that turns out to actually have a good quality, it will then see what the reward will be, and depending on whether or not it starts their Q learning, it will then figure out its future state and future action. It will then use what it learns from this to revise its policy. And then it will change the current state to the future state and change the current action to the future action, and then it will repeat this process until the resulting policy is satisfactory. Does anyone have any questions?
Also, I'd like to add inside the function, so you can see the actual symbols for what they are, the alpha and the gamma. So gamma refers to the discount factor. The discount factor is basically saying the more moves you make, which is the longer it takes you to solve the problem, those later moves are kind of discounted in their impact. And the learning rate is, learning rate from most machine learning problems. Models have a learning rate. So that's the same. Yeah, and any questions so far? Okay, I guess we can move on. So now it is my turn. My name is Jason, for those of you who don't know. To just kind of recap this whole information dump on the fundamentals of reinforcement learning, we have a small activity. We probably won't go through all 4 of them, but for the first one, a game of checkers, can someone try and label the environment, agent, and action, and observation and rewards of this problem of a game of checkers to see if we can match it to a reinforcement learning framework? You can say it out loud or type it in the chat. And you don't have to try and go for all 5 at once. If you think you have a good answer for one of them, then go ahead, share that as well.
So do we know enough about the environment?
So Gaston has a good guess, and basically the environment is the board, right? The board of the game of checkers that you're playing on. And that's a good answer because you interact with the board, right? You place pieces on the board and you try and take your opponent's pieces on the board. So that's a good answer for the environment.
Wait, Jason, did you hear Vincent's response through Emily?
I thought he was asking a question, so I was trying to answer. Or Vincent was. Did you answer, or was that a question, Vincent? Sorry if I misinterpreted.
Yeah, that was my answer.
Okay, yeah, then definitely.
Yeah,
like
I asked the question. Mm-hmm.
Oh, okay, good. All right, so we have the environment down. What about agent, action, observation, and rewards?
Like, would the game itself be in like environment as well, or is it just like?
Yeah, so you can, I guess, consider the game itself to be equivalent to the board of checkers. So basically, I think the game itself would be a more broad answer, but that's definitely acceptable as well. We kind of understand we're referring to the game of checkers through the board.
Do the rules of the game also fly under environment?
Yes, the rules of the game are definitely a part of the environment. So sure. Looks like Gaston gave a few more answers. So definitely an action is you moving your piece. And observation is the change in environment, definitely. So the more specifically, you basically look at the state of the board itself, like what pieces are where and how many pieces are on it. That's basically your observation of the game of checkers, right? And you can be rewarded for taking a piece. One thing I think we kind of forgot to mention is we kind of give reward a lot of positive connotations, but in the world of reinforcement learning, reward can be both positive and negative, right? So like Gaston said, you would get positively rewarded for taking a piece, and you would be negatively rewarded for losing one of your own pieces. So that's a very good answer, Gaston.
For the observation, is it pretty much just an update in the current state then?
Yeah, basically. Observation, when the agent makes an observation, it will generally get a new state from the board, from the environment, and also the environment will give it its reward. So those are the two kind of things it can take from observing the environment. Okay, so it looks like we kind of basically understand this problem. Let's just cover one more. So let's go for a more complex one, which is, I guess, playing a game of Fortnite. It doesn't have to be Fortnite, but we can just say Fortnite to kind of restrict our domain from all games to just a single game.
The environment is the game environment, so like the battlefield, I guess.
Yes, that is a good environment. Yeah, so Fortnite is a first-person shooter, so it has a battlefield, right? So basically, the whole battlefield is kind of your environment, and you can do stuff inside the battlefield.
Yeah, and the agent is your playable character. Actions would be like reloading your gun or picking up an item, shooting, whatever, walking around.
Yes, yes.
Observation is what you see on your screen at the time. Rewards could be your kill ratio, I guess, whether you win the game as well.
Yeah, definitely, definitely. So if you manage to defeat an opponent, you get a positive reward, but if you are eliminated from the game, then obviously that would be a very negative reward, right? So yeah, sounds like you guys have gotten it. So let's just move on to the next slide.
Hey, Jason.
Yes?
So, like, going back to the Fortnite example,
Okay.
what happens if there's a lot of, like, for the current state action space, if
Mhm.
there ends up being a lot of, like, neutral actions that don't directly lead to a positive reward or a negative reward? Would the AI just do a neutral action until something happens?
Yeah,
where it's
so
forced to make a decision?
definitely. So, you know, like we said in the beginning, everything is randomized. So you're basically taking random actions. So it may end up that you just, when you start the game with your random knowledge base, all you do is you just, you know, move left, right, up, down, and basically just run around in circles. And you're not necessarily getting rewards for that. But eventually, some other player is probably going to find you and eliminate you, and that will give you a negative reward. So now the model will associate all those random movements, like moving around in circles, will be associated with negativity, with that negative reward. And eventually, if it keeps making mistakes, it will hopefully start to move away from those random movements and start doing more good movements, like actually shooting its gun at an opponent. But that also brings up that very first question you raised in the beginning of the presentation about the whole sparse reward thing. How if you have a situation where you're very rarely going to get positive reinforcement, it will take you a long time to learn to do better, right? So that's a good question, Gaston. Any others?
On the previous slide,
Okay.
what do alpha and gamma mean again?
Okay, so Eric, could you go back a slide? Yeah, so like I said, these are kind of, you call them hyperparameters, like in traditional machine learning. They're kind of the default values you set to before you start your model. Gamma refers to the discount factor, which means you kind of want to discount the impact of moves made much later in the game from impacting your current score. So that's kind of like what we were talking about with the game of Fortnite. If you spend like an hour walking around in circles, the moves you make in the hour are probably not what contributed to your win or loss. It's probably the moves you started making in the beginning that, you know, really made a huge impact to whether you would win or lose the game. So this is kind of to reinforce the idea that you want to win early rather than, you know, doing pretty poorly for like an hour and then suddenly winning at the end because of a miracle. So that's what the discount factor is. You want to discount the much later moves you make to really emphasize the impact of the earlier moves you make. And the alpha is the learning rate, which is similar to the learning rate you'll find in other machine learning strategies.
Okay,
So
that makes sense.
Yeah.
The gamma, is that being multiplied to QS prime A prime, just that part? Or is it being multiplied by QS prime A prime minus QSA?
No, it's just the QS prime A prime part. So the gamma, one of the common gamma rates are 0.99. So that means every future state and action you end up in, the S prime A prime, will be 99% as effective. And you can imagine with that compounding on itself over like a bunch of different moves, like your 100th move will be like probably less than 1% as effective as your beginning move. So that's how that works out.
Okay, thanks.
Question?
Yes.
In the previous slide, why do we subtract QSA after gamma QS prime A prime, but then we also add QSA to the left of that addition sign?
That is a good question. So inside that little parentheses thing, when you're subtracting Q of S prime A prime, well, you're subtracting QSA from QSA prime A prime, you're basically trying to find the difference between your future state and your present state. So if you end up in a better future state than your current state, that difference will be positive. So good job, you ended up in a better position, right? But if you ended up in a worse position in the future, that will be a negative value probably, right? So that will negatively impact your reward. So that's why they do that.
Got it. And then the addition for QSA is just saying we're accumulating our reward, right?
Exactly. Yeah. So the QSA outside of the parentheses is just the Q value you were in previously. So that means your future state is derived from the Q value of your previous state in the end.
Gotcha. Thanks.
Good question. Good question. All right. I think we can move on if there are no other questions. Okay. So now we're going to get into policy gradients, which is the reinforcement learning technique, which our project is sort of using. Policy gradients is another reinforcement learning algorithm, of course. It's very similar to SARSA, but it utilizes a neural network to improve its policy. So SARSA is what's called an on-policy algorithm, which means it refers to its policy to pick its action. And the same thing goes with policy gradients, hence it's in the name. So it tries to use the neural network to improve its policy, as opposed to trying to use the Q function and Q table to try and influence that. And to improve its policy, it uses gradient ascent. So gradient ascent is very similar to what you may have heard of gradient descent, right? So traditional machine learning uses gradient descent to minimize its loss, its error. But here, with reinforcement learning, we want to maximize our rewards. So that's why we have to use gradient ascent instead of descent. We want to maximize the rewards we get from our policy. At the bottom, you'll see some mathematical representations of policy gradients. The symbol pi in this case refers to the policy. So the policy takes in it takes in the action and state. Well, actually, the policy will give you the probability of taking an action given you being in a current state. So that's what that whole representation looks like. It uses, statistics notation a little bit. And of course, the actions you can take are within your action space, so all possible actions. And the state you're in will be in the state space, which is all possible states you can be in. So yeah, and that's what the bottom image refers to. The policy of you taking an action given being in a current state is the probability that you take that action. Then there's that symbol theta. theta refers to the parameters. So since we're using a neural net, right? Neural networks have weights. So the parameters in this case would kind of be like the weights of the neural net. So given a particular arrangement of weights in your neural network, what is the probability you'll take that action given the states?
I have a question. So
Yes.
for when you said used to determine the best policy for the agent's entry into the environment, would you say that's like the same goal as a Q-learning and SARSA?
Yeah. So most reinforcement learning techniques have the same goal in mind, and that is to return the best policy for your agent to follow.
They just have different approaches on how to achieve that goal.
Exactly, exactly. Just like when you're classifying things, your end goal is to try and classify with the highest amount of accuracy, right? But the different strategies you take are where you differ in your techniques. Okay, if there are no more questions, let's move on. So here's some more maths. This is looks kind of complex, I guess. J is a function used to score our policy. So J is kind of trying to score our parameters to say, okay, is this a good set of parameters? Are we doing all right so far? The R of tau is kind of like the expected future reward. So given these parameters, what do you expect to receive in the end after doing so-and-so actions? And then the E of pi is basically the expectation of the policy you're following. So to sort of translate all this to English, J is trying to score your current parameters based on your current policy and what reward you expect to get in the future. Yeah. So this is a kind of like a general summation of how we're trying to score the policy. And at the bottom, that just shows how gradient ascent works. So the upside down triangle is the delta is the gradient symbol, and you're trying to find the gradient of your score function to use that to improve it. Alpha, of course, is the learning rate, and in gradient descent, you would see a minus sign between these two things. But for gradient ascent, we have to use a plus sign to try and maximize our rewards using gradients. And that just says the new parameters, the parameters from time plus 1 is equal to your old parameters with the gradient added to it. And that's why this is called policy gradients. I know that was kind of a lot to take in, so any questions?
Does this have a similar problem to, I think it was Q-learning, where you could end up going too slow before the next state update and you just fall behind?
Yeah, so this is actually supposed to, well, there's some, we'll cover this in the next slide, but basically for the state updates, everything happens in a loop, right? Which means nothing, your function really can't fall behind because it will always happen with each step of the state updates. What happens with Q-learning though, since you have to do all these calculations, is just that every single step will take a prohibitively long amount of time. But with policy gradients, this is kind of made in response to Q-learning and deep Q-learning, which is Q-learning with neural networks, and that it's trying to it's trying to update its policy more quickly than Q-learning does. Did that answer your question, Gaston?
Yeah.
Yeah.
So it usually doesn't have that problem, because I was thinking that if you are trying to do it and the hardware is kind of slower, it could just end up updating the gradients kind of slow, because it's always continuously updating the policy, right?
Yeah. So yeah, it happens in steps. So if your calculations take too long, you won't like fall behind in the steps. It's just that each step will take, let's say, a long time to step to the next one. Once you finish your calculations, then it'll step. Okay. So here's some more math for the policy gradients. This is basically a summary of what I just said. So the policy is represented with your pi theta, theta being your parameters. The function you're trying to improve with gradient ascent is the j function, which is the score function. So you find the gradient given your parameters of the j function, and then you use that to update your parameters. Yeah. All right. I think we can move on to next. So now we get into why we want to use policy gradients. So like I was saying to Gaston, the pros for policy gradients is it can converge faster than other algorithms. And that's because it's not reliant on the calculations of the Q value and the Q table. It just tries to use neural networks to improve its policy. And since it doesn't really rely on the Q value calculation, it performs much better with very large action and state spaces or continuous spaces. So with Q learning, one of the problems we highlighted is that if you have a lot of possible actions and a lot of possible states you can be in, you have to calculate a Q value for each pair. So if you have 1 million possible actions and 1 million possible states, then your Q table is going to be like 1 trillion different calculations you have to make per step, which is, as you can imagine, prohibitively expensive. So here we just want to try and improve the policy in one step. So like, okay, the policy tells us to move this way. Was that a good move or not? And then we improve the policy that way. And the third advantage is policy gradients can learn stochastic policies, while the previous ones we talked about have to stick with deterministic ones. So stochastic means instead of definitively taking this action when you're in this state, you have a probability of taking each action. So let's say in the game, right? If Q learning was to say, you know, always go right if you're against this wall, policy gradients would say, okay, you have, let's say, a 10% chance of going left and a 90% chance of going right. So it's more flexible. Now, the cons is that this is also vulnerable to getting stuck in local maximum and minimum. So with Q learning, the key advantage of it is that it always strives to reach the optimal state because it goes for the maximum. But policy gradients can get caught up in near optimal situations, so it might not reach the best performance possible for that problem. And of course, it is possible that, you know, policy gradients might not be the best technique to use in this problem. So it is your job as a machine learning, scientist to experiment and find the best strategy to use. But that applies to all strategies. So let's move on to the next slide.
Oh, before we move
Oh,
on,
yes.
what architecture does the neural net typically take? Like, is it a convolutional neural network?
It's a fully connected neural network. I'm not sure if they can take different forms, but the one we're using today is a two-layer. It has one input layer, one hidden, and one output layer.
Okay,
Yeah.
thank you.
Yeah, you probably can customize it somewhat, but in this project, it's fully connected. Okay, next slide. So yeah, this is just to quickly explain what a large action space is. So like I said, a large action space means there's a lot of possible actions you can take. And it doesn't have to be like unique actions. It can be something like this continuous action space where if you imagine you're driving a car, right? One of the actions you can take is turning your steering wheel. But the amount you turn your steering wheel is pretty much has infinite possibilities. You can turn it, 0.1 of a degree, 60.333 to something of a degree. The amount of ways you can turn your steering wheel is infinite. which is very disadvantageous to try and calculate with Q-learning. So, and with a game like Minecraft too, you can, move less than a meter, move like 5 meters, or turn your character 30 degrees to the right or to the left. So all these large continuous action spaces will make it very hard to calculate with Q-learning. And on the next slide. Next slide, Eric. Yeah. On the other hand, we have some problems that have small action spaces. So for the game of Space Invaders, really all you can do is move left, right, shoot, or stay still. So those are like 4 actions, which means it can be much more efficient to just calculate the Q values for each of those 4 actions and then figure out the best action to take from there. And with the game like Flappy Bird, all your actions, all your possible actions are to either flap your wings or not flap. So that's 2 actions, right? So that means it's even more easy to calculate the Q value. Oh, Gaurav is handling the slides. Okay, never mind. I didn't know that. Okay, so next slide, Gaurav. Yeah. Now we're gonna talk about the whole deterministic versus stochastic thing. So basically, in a deterministic approach, each state will determine a single action. And when you're in identical states, you'll always return the same action. So for example, if you're in a game and you're facing a wall in front of you, your move will always be to, let's say, turn right, right? You will always turn right when you are facing a wall. So that's what a deterministic approach would spit out. Whereas a stochastic approach would give you a probability. So you might have a 50% chance to turn right or a 50% chance to turn left, something like that, right? So you can see it's a bit more flexible in this regard. Any questions? Okay. Oh, yeah. So I'll just quickly wrap up what we have right now. So this is just an example of why a stochastic state would be advantageous. So in this case, we have a Roomba. We're trying to train to suck up the dust cloud in front of it. But to the left and to the right, we have some hamsters in the corner. We don't want to run into the hamsters with our Roomba. And then the black represents a wall, and also the boundaries represents a wall. So currently the Roomba can move left or move right. On the next slide, we'll see what happens with a deterministic policy. So all those arrows represents squares the Roomba can be in. So if the Roomba is in the middle square, right, in front of the dust, the optimal action would be to go forward and suck up the dust. But in the white squares, the optimal action would be to not run into the hamsters, but to go back towards the dust, right? Move right or left. However, we have what's called an alias state in the pink squares, where the state the Roomba is in is exactly the same. It has a wall in front of it, empty spaces to the left and right, and a wall behind it, right? So that's identical for both the pink slides. But since they're identical, but they require different solutions, if you pick one action, you have to carry it over to the other action. So the optimal move for the pink square on the left is to move right towards the dust, but then that transfers over to the pink square on the right, where the optimal solution would be to move left. But you already picked right, so it always has to stay the same. But if you have a stochastic policy, you can use a probability where you have a 50-50 chance of moving left or right. And that will break you out of the, the situation where you need to make the same move in identical states. Did that make sense, everyone? All right.
Cool. So I think that's our slides for today.
Yes. So
Let's jump into the code. So if has everyone been able to clone the repository? if you clone the repository, the Jupyter Notebook file will be in the Atari 3.7 folder, and it will be this one right here. Let me go ahead and actually pull that up. Cool. So these lines will be installing the packages that we'll need to use for this. Since I already have them installed, I'm going to remove them. So just as a little preview before we jump into explaining the code, this is going to be a explanation or a dive into how you can use a reinforcement algorithm on training an AI to play Pong. And that'll be trained specifically from the pixel data of the current environment. And so this code uses a framework called GYM. GYM is a framework developed by OpenAI, who is basically the leader in reinforcement learning work in industry. And so we'll be using that. Other than that, for the neural network part, actually this entire code is written completely in NumPy. So there will be a lot of bare bones code. So if you have any questions, please feel free to ask. There will be a lot of details in this code. So if you don't understand everything, that's completely normal. In fact, I didn't understand everything, and I consider myself fairly familiar with neural networks. So first I will just run this. Actually, first I will set this to true, so then we can run everything and check out what this code looks like.
I think you might need to show your whole screen.
Oh, am I not showing my whole screen? Let me do
It's just the Chrome window.
Okay, can you see my screen now?
Yeah.
Okay, cool.
Great.
So on the left side, this is the environment, and this is the Pong environment, and on the right of this is the AI we're trying to train, and obviously the AI is doing poorly right now. And on the left is actually the computer it is trying to beat right now. Spencer, you can go for it.
Okay. Hi, everyone. I'm Spencer. I'm part of the Reinforcement Learning Committee, and I'm a third-year computer science major. So basically, the code is broken down into a bunch of initialization or function definitions, and then it moves on to the main code at the bottom. So just to start off, we're going to go with the hyperparameters. We're going to go step by step. So H is basically the number of hidden layers, or the hidden layer neurons. And these are basically decided arbitrarily by the developer. And there's just enough neurons to basically train all the neurons and calculate the data set, but there's not too many that it will increase the training time. And then also next is the batch size, which basically 10 is the number of episodes that it uses before it actually updates the model. The learning rate was also talked about by Jason, but basically you're shooting for a learning rate that reaches an optimal solution, or the local minima or global minima, within a reasonable amount of time. Gamma is the discount factor for the reward, which basically, what I could say about that is it weights every move that the Pong agent makes. And if you look at the picture down below, right, the up, down, up, down, down, it shows games that have a various amount of move numbers. And basically, it encourages the games with the least amount of move, because those will be weighted more. If there is a game that goes on for maybe 100 moves, it will be less discounted, because those increased amount of moves will be considered more noise, because it's not necessarily going towards a win. It's kind of just laying stagnant. And then the decay rate is part of the basically the optimization optimization function, and that'll be basically explained a little bit later. And then where Gaurav was talking about the config flags, the resume, that's just to basically if you want to use a pre-trained model. And then render is just to see the Pong window that you see in the top left.
Yeah, so I'm actually going to shut the render off because it's actually slowing my computer down. And so give me 1 second and then you can continue your explanation. And then I can let it run while that happens. Yeah, cool. Go for it.
Okay. Any questions on the hyperparameters or any of the libraries?
Does Gem provide, as a framework, a way to define like a custom environment?
Yes, you can define your own custom environments. Yeah, it's basically like an interface, and then you have to implement a bunch of these environment methods that are required.
Yeah, so to answer your question, you can, there's a bunch of environments they provide. I believe you can also customize them and use them using the gem make function.
Mm-hmm.
Any more questions? All right, I'll move this over to Pushpal. She's going to explain the next couple blocks of code.
All right, so here we have the model initialization. So first up, we have the two weights here that we're going to define. W1 are the weights between network, I think 1 and 2. And W2 is, let me see, I actually thought that this was Spencer's part. I'm sorry.
That's okay.
Yeah, W2 is weight 2. Then we have the buffer and the RMS proc cache. Cache will be explained later. Moving on to the sigmoid function. The sigmoid function is basically an activation function, and it takes the given value and returns a value between 0 and 1. This is basically a probability as an output. And then we have prepo. Prepo takes in an image and returns a 1D float column vector. Throughout the function, it basically crops out the excess and leaves you with the main components of the game. So in this case, it would be the paddle and the ball on both sides. So it does this by assigning I to either 0 or 1. This is like a binary way to differentiate between what is at work and the background. So that's how you get this like grayscale kind of look. And basically it returns that array. And then we move on to discount rewards, which takes in a 1D float array and returns another array of the discounted rewards. It iterates through the float array and resets the running add to 0. And using the running add, it calculates the discount reward by multiplying it by gamma and adding that to the discounted reward array. So yeah, it discounts per batch, not per move. So that's why you have an entire array passed in. Yeah, that's it for those 3 functions. And then we have policy forward.
Okay, I'll talk about the policy forward. So basically what policy forward does is that it takes in the observation and it returns the P, which is going to be the probability of going up, as well as the hidden state. This hidden state is basically used as memory between different neuron layers. And just to go through a little bit of the code, basically the hidden state is calculated by doing a dot product between the observation and the weight 1. And then from there, using that hidden state, it does another dot product with weight 2 to basically move it through the layer. And then it produces this log probability value. And from there, you use the sigmoid function to put it between 0 and 1 to create that probability. And just to highlight what's going on in the image below, it's basically the forward propagation. So taking in the image and a couple parameters, it basically shoots out the log probabilities that you see there to use for the action.
Yeah, and so I will talk about a backward prop here. And just as a visual, this is kind of what the neural network will look like as an architecture. So you'll take in the input as a pre-processed image, and you have a 2-layer neural network. And so this will be weight 1 that Pushpa was referring to, and this will be weight 2. The output will be the probability that the agent should move up. Yeah, that will be the output. So for policy backwards, you're basically going to take the derivative of the log probabilities and take a dot product of with the hidden state probabilities, and then you'll calculate, and then you'll do a back prop ReLU, and that will basically take care of the activation function, and then you'll do another dot product, and that'll give you the derivative of weight 1. And so essentially taking the back prop of this. For more details, you'll probably want to consult. There's probably better literature that will explain this. Any questions up till this point, actually? We could stop here. So this is, thus far we've covered the hyperparameters and all the functions that we'll be using. So if anyone has any questions, this would be a great time to stop.
When do you know that you're done training?
So like, you will be done training when you're satisfied with the agent's performance. So like, so to give you an idea, the current model that we're training right now, it takes approximately on the order of 10,000 actions for you to get some kind of reasonable output. So like it kind of, so we actually haven't been able to train it that much, but if you want to like get better than like somewhat good performance, then you train for longer. So it's mostly like eye tests, depending on what your desire and your outcome is.
Yeah, I'll add on to that. So reinforcement learning generally is it's a continuous training like method. So basically you keep training for as long as you can until you feel like your model is performing adequately. So for me, I've been training the model in the background, and I've trained it for, I think, around 5,000, 6,000 episodes. So right now it's performing a lot better than it did before. So I can show you guys that at the end of the presentation. But yeah, but now that it's doing like not terrible, all the training episodes are taking a lot longer because, you know, the games are lasting longer because our AI is performing better. So it definitely slows down the training process once you get better at once your AI gets better at the game.
Any other questions that anyone might have? Keep in mind, this is very bare bones code, so if it looks very scary, that's fine. This is not what PyTorch looks like.
So it's basically successful only if you basically converge on like what the policy ends up becoming, or converging towards a certain policy.
Sorry, could you ask your question again?
Yeah, because I remember I was reading the term about how like the algorithm would start converging towards a specific policy. So there's but if it doesn't converge, does that mean you just don't have anything useful?
Yeah, so if it turns out that, you know, after 10,000 or so episodes and your AI isn't performing any better, then that's probably something, an issue with your model, right? But for this one, it does get better, but the reason it starts out very slowly is because since Pong is such a complicated game, it's very hard for your AI model to randomly score a win, against a trained AI, right? It's very, very rare, which means it starts off having a very hard time training itself to be better at the game because it doesn't really have any positive reward to tell it that it's doing well, right? But eventually, on the off chance of randomness, it will manage to score a goal, and it will use that to improve its policy. And then, through all these random training moments where it, gets lucky and scores a few wins, it'll try and learn to do better. So yeah, it will eventually converge on a policy that allows it to beat the AI,
So like,
given enough time.
how would you know? Yeah, how would you know if you're
So I
Well,
think
you would know because so what was your question? How would you know when it gets better?
yeah, like how would you know like let's say you don't, it's not improving at all, but like how do you know if it's like it just needs more time as opposed to like it's just never gonna work?
Oh, that is a good question. You
I
just
would, yeah, go ahead,
yeah.
Jason.
I was just gonna say it's just up to experimentation at that point, I guess. So yeah, what were you gonna say, Gaurav?
Yeah, I was just gonna say it's probably a matter of judgment. Like if you know that you're using a network that has worked before, and you can, that becomes a debugging question, right? Like why is this not working? There's many factors to it, and it's about figuring out what it is and what it's not. So it's less a theoretical question, more of a how am I gonna go about fixing this problem?
Yeah, it's just the problem that all computer scientists face at that point, I believe. But good question.
Great question, actually.
I have a question. So it seems like learning from scratch takes a really long time. I remember that OpenAI, when they trained their Dota game thing, I think they trained it on some human games, right? So what type of reinforcement learning is that, where it can learn from examples from humans?
So that would probably be similar to just transfer learning, like from traditional machine learning. So maybe they had some predefined notions on how the AI should perform. So they were able to use that to influence their technique to make the gameplay better initially. So I'm not familiar with which strategy they actually used. So I wouldn't know how to answer that. But yeah, it sounds like they were able to transfer some prior knowledge to their AI to help it perform better in the first place.
Yeah, maybe it's imitation learning, perhaps.
Oh, okay. I'll have to look into that, but that sounds pretty cool.
Cool. If we don't have any more questions, we can go ahead and move on. Take it away, Spencer.
Okay, so this is basically the main part of the code. After all the setup's done, this is where all the calculations are basically done with the actual values. So I'm going to cover the first 3 lines of this because the next, I guess, 5 are going to be explained throughout. So basically, the environment is made in the gym make, and Pong is a preset game that is already within the gym library. And then the wrappers.monitor is actually just, it's I guess, an offshoot of the gym library where you can record it as an MP4 file.
Mm-hmm.
All right, so going down. So while true, basically I think this answers some of your questions where when does it stop? It doesn't. Yeah, until the developer makes it stop, I guess. The render is if the render is true, you can see it. And then the current X, that prep-pro observation, is basically using that prep-pro function to create an image that the computer can process.
Prep-pro stands for pre-process, in
Yeah.
case no one caught up.
Yeah. And then below that, you take the previous, you basically subtract the difference between the previous. And if there is no previous, you just start it out, it just zeroes out the X.
Mm-hmm.
And I guess you can see it above. I think the image is up there still, the gray image. Yeah.
Yeah.
So basically, There is a couple streaks that you can see within each image. That's basically the difference between the ball moving from one area to another. If you could scroll back down, just for visual representation. But from there, you get the X value and you input it into policy forward, which gets you the probability of moving up as well as the hidden state. And then this is where the stochastic part of the program comes from. Just to read it out, it becomes 2 if this random number generated is less than the probability. So the stochastic part comes out at, let's say the probability is 0.8 or 80%. Technically, that random value could get to like 0.9 or 0.96. And even though the probability of moving up is 80%, it will still move down, which is the value of 3. And then once that is taken out or done, it appends basically the observation in the hidden state within those 2 respective areas or stacks. And then this is where the supervised learning, the fake, I guess not necessarily supervised learning, but since it's not supervised learning, it creates a fake label. And basically this label is to, what it's been used as is basically to distinguish between encouraging moves and discouraged moves. So this is later used for the loss function, but basically that it appends it the y minus a prob. That's basically the value that it's either encouraged or discouraged in future states. And then one of the functions that we get from the gym library is step, and that's where you get the observation, reward, done, and info. Observation, reward are, I guess, self-explanatory. Done is if it's finished with this episode, and then info is basically just diagnostic information. And then at the end, it basically adds the reward to the reward sum, and it appends it to the DRS variable.
Any questions?
All right. Oh,
Sorry. Any questions here? I'd like to highlight this. I think Spencer did a great job of explaining this, so I don't really have anything to add. But this is where the stochastic part happens. So this part will actually allow the agent to explore the environment, basically letting it do actions in spaces that are not necessarily recommended by the neural network, but it is there so that the agent can explore the environment. And this fake label is created, and the word fake is there very, the word fake is useful here because we're not doing supervised learning, but it is used to calculate the loss. And this dlog ps is going to store the derivative of the cross entropy loss here, and that becomes y minus a prob. Yeah, go ahead, Pushpa.
all right. So this part of the code is basically when the episode is finished. So if done, it counts the episode number, adds it by 1. This is where Jason was talking about. He was running it for 6,000 episodes and was just barely starting to train. Yeah, so this is that. Below that, you see all the stack variables. That's where the code is basically storing all the data for that game and preparing for the next by resetting the array memory. And then you move on to calculating the discount reward. You compute the discount reward by going backwards, basically. It also accounts for loss. So that's where the variable EPD log comes in. You calculate the discount reward and multiply it into that variable to calculate it with the accumulated loss and backpropagate. So that's where policy backward comes in. And then you move on to updating every episode for each batch size. So here you iterate through every batch set and you get our gradient buffer values and use it to calculate cache for each item. I'm not sure if you remember, but I said that cache would come up later. This is where it comes up. It's used to save memory of RMS prop, and it's basically deciding which way to go. RMS prop cache with the array k, it's the k times cache gives you the current info of the optimizer. So then you update your weights and reset your batch's gradient buffer, and that's how the game episode ends. So it's basically resetting everything, refreshing, storing data, and preparing for the next game. And then that's where boring bookkeeping comes in. Yeah.
So just to expand on what Pushpa was saying, so here you have the discounted rewards, and here you do this is kind of like a batch norm layer, like was covered in the GAN workshop, where you subtract it by the mean, so you have a 0 mean and a unit variance. This helps with kind of robust training. And then here you multiply the difference of log probabilities by the discounted rewards, because when you do policy backward propagation, you do need to take into consideration the loss as well as the reward that you accumulate. So that is why that happens. And then you calculate the gradients, update the gradients in the gradient buffer. This RMS prop is basically the optimizer. If you want more details about this, you should probably consult some kind of tutorial on RMS prop, but that's just the bare bones function of it. Then here you update the model weights using the learning rate gradients and the optimizer's recommendation of which direction to go. And yeah, that's what these portions do. And then here, just to finish it off, you have some bookkeeping that you do, the running reward, and you print some function. And this is kind of what your output looks like. So obviously, in the first episode, the AI is doing terrible. All of the rewards are -1, implying that it has not won a single, point. And here, whenever it does become, whenever there are exclamation points, that means it finally won one. And so here, let me go all the way down to see how the AI is doing now. So yeah, it's at episode 264, and it's still not doing so hot. So this is a running mean, which basically means it's basically winning about 1 point every game, which is pretty bad. And like we said, this takes a long time to train, so not going to be able to see immediate rewards, but it is getting better.
Yeah, go ahead.
That's about it. That's about all the code we have to cover. Any questions, comments, discussion, anything?
Can we see Jason's results?
Right. So I'll just,
You can share.
yeah,
Cool.
let me set it up. You can keep talking while you do it.
Yeah, so yeah, Open Gym has a lot of cool environments you could use. So there's one called Cartpole, which basically tries to get a pole to stand, and the pole has the action space of going left or right. And so you're basically trying to train the AI to not fall over, essentially. So it's a really cool framework that I would recommend you try to learn. It's pretty easy to learn if you want to get into it. Any questions?
For these models, does it transfer over? So like, I don't know if this was mentioned, but I think Google's AI that they taught to play Go, they taught it something else, and it learns like very, very quickly how to win at that game as well. Does that also apply to these reinforcement learning models? Like you can just teach it another game relatively easily?
So I mean, I would say that I wouldn't know exactly. There's a high probability that, yeah, you can transfer this knowledge over, just because if you're using neural networks are able to transfer knowledge over from one domain to another. but I can't say with absolute certainty. I do know that there is research being done on transfer learning for RL tasks.
Right. It hasn't been as straightforward as computer vision transfer learning, but there was a paper released by Google quite recently about, I think on Atari games as well, where they just trained the network to play on one Atari game and it could transfer to other ones. And it was like I think it was a significant breakthrough because they hadn't been able to do that type of transfer learning before. It's a good question.
Sorry, guys, having a little technical difficulties trying to get it brought up.
So yeah, give it up for the RL committee. They did a great job. They spent a lot of time on learning this material and learning how work works to actually explain everything. So yeah, kudos to the RL committee.
Good job, guys. Okay, I finally got it to work. So I'm going to start sharing my screen. Oh, the host has to enable screen sharing for me.
Yeah, go ahead.
Oh, okay. Let me do that.
Okay, I think I got it.
You got it? Okay.
All right, is everyone able to see?
Yes.
Okay, so yeah. So this has been training for about 6,000 episodes. So each episode is basically a 1st to 21 match, which is why you saw Gourov's running mean as somewhere close to negative 21. That means the computer that we're playing against has basically scored 21 points against our AI, basically. Maybe it's won once or twice, but now you can see in the score board on the top here, our AI is actually scoring a lot more than once or twice, and you can notice that it still looks kind of random to me. It's like moving up and down really jerky a lot, but it's still trying to hit the ball, and here it's actually in the lead, but it probably won't be able to keep that lead for long.
Low key, that's how I play Pong.
Nice. Yeah.
By the way, Jason, can you move the thing on the top of your screen? I think it's blocking the
thing.
score.
Yeah, it's the Zoom like top window. I don't know how to minimize it actually.
Oh, sure.
You can just minimize the actual window of the game.
Yeah. Okay, yeah, you're right. Yeah. So can you see it all now?
Yes.
Okay. Really quickly, I'll just get off from the game for now and look at the whole output from the score. As you can see, all the exclamation marks means it's scored a point. But of course, since it's to the 1st to 21 points, now that my model is performing so well, each episode is taking way longer to train because the games are lasting much, much longer. But as you can see, the current mean is, I think it says 9. So that's a marked improvement from minus 21, right? But every now and then it'll still have a very long losing streak, as you can see. But, give it a 4,000 or so more episodes, it'll probably get much more decent.
Cool. So I think it's interesting how the computer AI is probably like very naively programmed, right? Whereas the reinforcement learning agent is still just comparable to the traditional AI. That's probably because we're using like a very simple reinforcement learning algorithm, right?
Definitely. So
yeah,
go ahead.
Less the algorithm, and probably that we're only using a single layer.
Yeah.
So it can only learn so much with a single fully connected layer.
True. And also, oh, this one is actually getting kind of close. Is it? Oh no, it lost. Oh, that's too bad. Anyways, yeah. So this is also brings up the issue that Gaston brought up at the very beginning of our presentation, the whole sparse reward problem. So in the very beginning, our AI is kind of bad, as an understatement at Pong. So it's very, very hard for it to manage to score and get a positive reward. So that really, really limits the amount that it can train itself, because it basically has to make random movements until it scores enough to learn. So that's probably one of the issues contributing to how slow its progression has been. So maybe if we can find a better way to dole out rewards, it would train faster.
Cool.
Yeah. But I mean, right now it's playing a lot better than I can play. So I don't know if I can criticize it that much.
Cool. Well, thanks very much for the presentation and the workshop.
Oh yeah, this model has been packaged by Pickle, so I can probably share it with you guys if you want to like see the, you know, the trained performance for yourself.
Yeah, that'd be cool. Cool. Well, thanks for the presentation.
It was a lot of fun.
Yeah. Cool. And just again, a reminder that we are still recruiting for officers. So that's 2 people for the outreach, and we're also looking for more committee leads. If you're interested, please let us know. And I think that's it for today, right?
Yeah, thank you for coming out. Have a good luck with finals, and we will see you back next week.
Stay safe.
Cool. Thanks very much.
Oh no, is it gonna lose this one? Oh man.
Wait, hold up. We got it. Come back.
Oh. Wait. Okay,
All right.
see you guys next week.
Thank you, everybody.
Yeah.
Thank you.
Bye.
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 Have a good weekend.
Yeah, you too, everybody. All right.